Introduction Refrigerant Selection Training Module. At the end of this module, you will be able to list desirable characteristics for refrigerants in vapor compression refrigeration systems. Explain the properties of and differences between CFC, HCFC, HFC, HFO, and natural refrigerants. Describe how refrigerant identification numbers and safety classifications are assigned. Describe compatibility considerations for refrigerants, oils, and system equipment. And list safety guidelines for the handling and use of refrigerants. The following factors influence refrigerant selection: physical, chemical, and thermodynamic properties. Refrigerants must be able to readily absorb and release heat, flow easily, evaporate or boil at or below the desired temperature in the refrigerated space, and condense above the temperature of the fluid in the surrounding atmosphere. Compressor type. The compressor must be able to handle the volume of vapor refrigerant that is flowing to it. The compressor design, system capacity, and density of the refrigerant gas must all be considered. Safety. It is desirable for refrigerants to be stable, non-toxic, non-corrosive, non-flammable, non-explosive, and non-reactive with water. They should also not contribute to ozone depletion or global warming, and leaks should be easy to detect. 3 common types of refrigerants are chlorofluorocarbons, or CFCs, which contain chlorine, fluorine, and carbon. Hydrochlorofluorocarbons, or HCFCs, which contain hydrogen, chlorine, fluorine, and carbon. And hydrofluorocarbons, or HFCs, which contain hydrogen, fluorine, and carbon. CFC and HCFC refrigerants were widely used in the 20th century because they are relatively inert, non-flammable, and non-toxic, which make them much safer than early refrigerants like ammonia, sulfur dioxide, and methyl chloride. However, CFCs and HCFCs are being phased out because it was discovered that they have both high ozone depletion potential, or ODP, and high global warming potential, or GWP. HFC refrigerants do not contain chlorine, so have zero ozone depletion potential, but they have high global warming potential, so are being phased out as well. As environmentally friendly alternatives are sought, new refrigerants are being developed, and some old refrigerants are coming back. Most refrigerants are made up of 5 kinds of atoms: carbon, hydrogen, fluorine, chlorine, and bromine. They are assigned identification numbers based on their composition. A refrigerant's ID number either follows the letter R for refrigerant or a combination of letters representing the atoms present, and it can contain from 2 to 4 digits. In refrigerant ID numbers, the digit on the far right represents the number of fluorine atoms. The second digit from the right equals the number of hydrogen atoms plus 1. The third digit equals the number of carbon atoms minus 1. And the fourth digit represents the number of unsaturated carbon-carbon bonds. Digits that are equal to 0 are usually omitted. For bromine-containing refrigerants, the letter B is added to the end of the number, followed by the number of bromine atoms present. For cyclic derivatives, the letter C is added ahead of the number. The number of chlorine atoms must be calculated. It is equal to the total number of atoms that can be connected to carbon atoms. 4 for methane derivatives, 6 for ethane derivatives, and so on, minus the total number of fluorine, hydrogen, and bromine atoms. Based on these rules, a molecule of refrigerant R22, or HCFC 22, has 2 fluorine atoms, 1 hydrogen atom, and 1 carbon atom. One carbon means that it is a methane derivative, so it can have 4 carbon-connected atoms. The number of chlorine atoms can then be calculated as follows. 4 carbon-connected atoms minus 2 fluorine atoms minus 1 hydrogen atom equals 1 chlorine atom. This means that R22 refrigerant is CHClF2 chlorodifluoromethane. Blends of 2, 3, or 4 refrigerants are assigned 400 and 500 level refrigerant ID numbers, or they can be identified by their individual ID numbers and percentages. So a blend of 75% R22 and 25% R12 can be identified as R501 or as R2212 7525. A letter is added after the refrigerant ID number if blends with differing percentages are available. For example, R401A, R401B, and R401C contain the same refrigerants but in different percentages. 400 and 500 series refrigerant blends separate or fractionate during the refrigeration cycle because the different refrigerants have different boiling points. This leads to multiple vaporization points referred to as temperature glide, among other things. American National Standards Institute, or ANSI ASHRAE Standard 34, assigns safety classifications to refrigerants. Each classification consists of a letter indicating toxicity and a number indicating flammability. For refrigerant blends, the safety classification represents the worst-case fractionation of the blend. They are assigned as follows. Class A refrigerants have not been identified as toxic at concentrations at or below 400 parts per million by volume. Class B refrigerants have provided evidence of toxicity at concentrations below 400 parts per million by volume. Flammability classifications are based on flame propagation, heat of combustion, the amount of heat given off when the refrigerant burns, lower flammability limit, or LFL, the lowest concentration at which a mixture of refrigerant vapor and air will burn, and maximum burning velocity, how quickly the flame travels. Classification 1 is given to refrigerants which exhibit no flame propagation, while 3, 2, and 2L are assigned to refrigerants that are highly flammable, less flammable, and mildly flammable in that order. CFC refrigerants were first synthesized in the late 1920s for use in large commercial applications. They were designed to be safer than previous refrigerants like ammonia, sulfur dioxide, and methyl chloride. They have lower boiling points, low toxicities, and are generally non-reactive. However, in the 1970s, scientists determined that the chlorine from CFCs that had accumulated in the upper atmosphere was destroying the ozone that protects us from harmful ultraviolet UV radiation. This has created ozone holes at the Earth's poles, where temperatures are low enough for ozone-destroying reactions to occur. Due to their high ODP, ozone depletion potential, and high GWP, global warming potential, which will be discussed next, the intentional release of CFCs became illegal in 1992, and their manufacture mostly ended in 1995, with a few exceptions. However, the stability of these chemicals and their long atmospheric lifetimes mean that the damage to the ozone layer will take a long time to repair. A refrigerant's ozone depletion potential, or ODP, indicates its ability to destroy ozone in the Earth's upper atmosphere. These values are relative to the ozone-destroying ability of trichlorofluoromethane, R11, which has the highest ozone depletion potential amongst traditional refrigerants due to the presence of 3 chlorine atoms in its molecule. R11 has an ODP of 1, and other refrigerants have ODP values less than 1. A refrigerant's global warming potential, or GWP, indicates its ability to trap heat in the Earth's atmosphere for a specific time period, usually 100 years. These values are relative to the ability of carbon dioxide to trap heat. A refrigerant's GWP value depends on its infrared radiation absorption properties and its atmospheric lifetime. For perhaps obvious reasons, it is desirable for a refrigerant to have both a low ODP and a low GWP. Common CFC refrigerants include R11, used in low-pressure centrifugal chillers to produce chilled water for air conditioning or AC systems. R12, before 1992, widely used for automotive AC and light commercial and residential refrigeration. R13 and R503, used in very low-temperature applications, usually cascaded with higher temperature systems which provide the correct condensation temperatures for the low-temperature systems. R113, used in small commercial centrifugal chillers, also as a cleaner for electrical equipment. R114, used in centrifugal chillers for AC and industrial cooling, for AC in very high ambient temperature conditions, and due to its stability in chillers for marine applications. And R115, blended with R22 to produce R502, which is used in low-temperature refrigeration systems. HCFC refrigerants contain fewer chlorine and fluorine atoms than CFCs, so they break down faster in the atmosphere. They still affect the ozone layer, but not as much. Unfortunately, HCFCs have high GWP. Examples of HCFC refrigerants include R22, at one time the dominant refrigerant in residential and commercial AC units. R123 and R124, replacements for CFC refrigerants R11 and R114. Both are used in centrifugal chillers. R124 is also used in high ambient temperature applications. And HCFC blends, like R401A, R401B, R402A, etc., designed to replace R12 and other CFC refrigerants. Like CFCs, it has been illegal to vent HCFCs to the atmosphere since 1992. HCFCs are scheduled to be phased out in many countries by 2020 and in all countries by 2030. Most HFC refrigerants were designed to replace a specific CFC or HCFC refrigerant. HFCs are chlorine-free, so have zero ODP, ozone depletion potential. However, they have high GWP, global warming potential, so are beginning to be phased out. Common examples include R134A, replaced CFC refrigerant R12 in many automobile AC and domestic refrigeration systems. R404A, introduced to replace CFC and HCFC refrigerants R12 and R502, used widely for transport and supermarket refrigeration, also for cold storage and industrial refrigeration. R410A, replaced CFC refrigerant R22 in domestic and commercial refrigeration units. Hydrofluoroolefin, or HFO refrigerants, have been developed as a replacement for HFCs. HFOs have zero ODP and very low GWP. They are stable, safe, and non-toxic, and can replace HFC refrigerants in many systems with very few design changes. Natural refrigerants are chemicals that exist in nature. However, this doesn't guarantee that they are safe. The very first refrigerants used in the vapor compression refrigeration cycle were natural, but they were largely replaced due to toxicity, reactivity, and/or flammability issues. Natural refrigerants are now making a comeback due to their favorable environmental characteristics and technological advances that help mitigate their health and safety hazards. However, system design, maintenance, and continuous monitoring are critical to the safe use of many natural refrigerants. Hydrocarbons, or HC. Hydrocarbons like propane and isobutane were phased out for flammability reasons. They have good heat transfer, and their refrigeration properties are similar to HCFCs and HFCs. Hydrocarbon refrigerants are currently used in domestic refrigerators and freezers in Europe. Carbon dioxide, or CO2. Carbon dioxide lost favor because it requires very high operating pressures and has a high compressor discharge temperature. However, these drawbacks can be advantageous. The high pressure means high fluid densities in compact systems, and the high discharge temperature can be used in external heating applications. For example, quick defrosting of automobile windshields and hot water heating in homes. Ammonia, or NH3. Anhydrous ammonia has seen continuous use as a refrigerant since 1876, in spite of its drawbacks, due to its excellent heat transfer characteristics. Ammonia's drawbacks include toxicity, flammability at some concentrations, and potential explosivity in enclosed spaces. However, ammonia is readily available, low in cost, and has a strong odor, so leaks are easy to detect. The energy efficiency and compact sizing of ammonia refrigeration systems has led to their use in large industrial and food processing installations. Air. Air is used as the refrigerant in air cycle refrigeration systems. In these systems, air does not change phase. It remains a gas. The lack of phase change dramatically reduces the amount of heat that is transferred. The low efficiencies of these systems leads to their use in only certain niche applications, such as aircraft cabin air conditioning. Water, or H2O. Water has several properties that would make it a good refrigerant. It is readily available, cheap, non-toxic, non-corrosive, environmentally friendly, and has a high heat of vaporization. In other words, it absorbs a lot of heat when it boils. Unfortunately, it has a high boiling point temperature at atmospheric pressure. The extremely low pressures that would be required to lower water's boiling point to a useful range, high vapor volumes, compressor design challenges at low pressures, and high compressor energy requirements are the reasons why water is not used as a refrigerant in vapor compression refrigeration systems. It is important to consider the compatibility of refrigerants, oils, and system equipment, especially when changing to a new refrigerant. Here are some guidelines. Mineral oil or synthetic oil is typically added to refrigerant to lubricate the moving parts in the compressor. Always use an oil that is compatible with the refrigerant and the equipment. When changing to a refrigerant that uses a different oil, a lengthy flushing is required to get rid of all traces of the old oil. Use separate hoses, gauges, and recovery equipment to avoid contamination. System piping, valves, and fittings may need to be changed if they are not compatible with the new refrigerant or new oil. Water contamination in anhydrous ammonia systems will lead to corrosion of brass, copper, and bronze components, in addition to lowering system efficiencies. Water can enter as vapor in air or via tube leaks in water chillers. Monitor systems for water and air leaks, especially those systems that run under vacuum. Purge air from the system as necessary, and follow proper procedures when performing service or maintenance to minimize air infiltration. Before using or handling refrigerants, review their safety data sheets, SDSs. Also, follow all recommended procedures and safety guidelines, including make sure that all personnel who handle refrigerants have been properly trained on their potential hazards, safe use, and proper handling. Wear the proper personal protective equipment, or PPE, when handling refrigerants or servicing a refrigeration system. Avoid skin contact with liquid refrigerants, as this can lead to frostbite. Even the safest refrigerant can displace enough oxygen in a confined space to cause suffocation. Follow the current approved confined space entry procedure, including ventilating or testing the atmosphere and wearing the proper respiratory protection before working in a confined space where a refrigerant leak or release is suspected. Never fill refrigerant cylinders over 80% of their capacity. High temperatures can cause cylinders to burst if there is insufficient room for thermal expansion. Make sure cylinders are not damaged and properly labeled prior to filling, and never mix refrigerants inside cylinders. Always charge refrigerant into the low-pressure side of the system. Charging into the high side could damage the compressor or cause a rupture in the system. And to minimize refrigerant release and exposure during filling, use proper recovery procedures, including clearing of hoses. Now that you have completed this module, you should be able to list desirable characteristics for refrigerants in vapor compression refrigeration systems. Explain the properties of and differences between CFC, HCFC, HFC, HFO, and natural refrigerants. Describe how refrigerant identification numbers and safety classifications are assigned. Describe compatibility considerations for refrigerants, oils, and system equipment. And list safety guidelines for the handling and use of refrigerants.